Good afternoon, everyone. Happy Monday. So let's continue with our lecture, this time with Chapter 15. Can you hear me okay? Adriana, am I sounding okay? Thank you. So today is March 15th. So let me give you some announcements here. We're on Chapter 15. So let's have our homework for Chapter 15 due next Monday. So we'll try to use this week to finish off this chapter we're currently on. So turn that in, upload it, and I'll put in the 10 points, as well as start working on Quiz 3. That will be when your next test is due. I'm guessing the next test, Test 3, will be in a couple of weeks. So start working on your Quiz 3. And lab report, if you've done it, I think only one person did the lab, so he was my partner. And so if you want to turn that in this Friday, you can turn it in. If not, do it this Friday. Come do it in person. So lab report this Friday. And it was on Le Chatelier's principle. So come to the lab and do the lab report and turn that in. We have 2-week period. Last week was Le Chatelier's. We also have this week to do that lab as well. And I think this is all that I have in my mind for now. Continue to do those clutch prep drills. If you do everything, A to Z, whatever they assign you, I'll give you some extra credit points at the end of the semester. The semester is ending, I believe, April 27th or so. So continue to do the grind and don't fall behind. So where we left off, we're continuing our discussion on pH and POH. Remember, we're talking about acid-base chemistry. So pH is really another way of telling us what the hydrogen ion concentration is. The POH is just another way of telling us what the OH minus concentration is. So these are scales. Okay? These are just scales. All right, so here's some equations. So make sure you know these equations. I'll give these equations on the exam, but I really feel it's best to know them. It will help you out in the future chemistry classes or just in future science classes as well. So here's the list of equations. Here's another equation here that we've gone over. So basically a list of equations for us. And once again, I would recommend you know them or you memorize them, because you'll see them not just in this class, but you'll see them in future classes as well, particularly in the other science courses. Right. Here's another equation here that we will use, percent ionization. We will see this again. Here we're talking about weak acids. Okay. Weak acids. So weak acids have an ice table that's associated with them. Okay. So this tells us how much did the weak acid go in the forward direction. Okay. How much did the weak acid go in producing protons? So remember our equation for a weak acid, it's going to be this. It's a weak acid, so don't forget the back and forth arrow. Acids do what acids do, and they give off a proton. Acids do what acids do, and they're going to give a proton away. And when they give a proton away, they generate acid, H3O+, same thing as H+, and they generate the conjugate base. Okay, so weak acids Some of these will go, what, 50%, 60%, 70%, 20%? It depends how weak the acid is. Okay. All right, so we'll see this again in a couple of pages in our notes. Okay, we will see again. So this would be the equation for a weak acid. All right, I'm going to move on to the next page here, you guys. So just telling us a little bit more about the idea of pH and pOH. So pH is a scale, okay, just like pOH, it's a scale. pH scale, pOH scale. And remember, our general equation is this: pH is equal to pH plus pOH is equal to 14. And again, that little p stands for power. Okay, power, the power of H. The power of H is minus the log, the concentration of H plus. The P power of OH minus the log of concentration of OH minus the hydroxide. Okay? The power, that little p stands for power, minus the log of anything. Okay? P of something is minus the log of something. On to the next page. Right, so like anything, pH is a scale, and here are some everyday substances that have a corresponding pH. You can also just as easily say corresponding pOH, right? Because pH plus pOH is equal to 14, but we generally use pH here. So even things, you know, as someone who teaches biochemistry, you know, your stomach acid has a pH. Okay. Urine has a pH. So if your urine is above a certain pH, that could be a disease. Okay, if it's below a certain pH, that could be a disease. Saliva has a pH. Okay, so tears have a pH. Blood has a pH. Okay, have you heard of the disease acidemia? Okay, acidemia is when your blood pH gets too low. So all of them have some sort of symptoms associated with it. Right, so almost anything can have a pH. It's a measurement of hydrogen ion concentration. The pH meter measures that. We actually have a pH lab that we do. I don't know if we're going to do it this semester because of the pandemic, but we have a pH lab that Gen Chem students usually do. They just play around with a pH meter. Another thing that's important here is our scale, okay? I want to emphasize to all of us that we're talking about a pH scale. So 7 is considered neutral, and this is acidic. Okay, being below 7 means that your hydrogen ion concentration is acidic, more acid than base. And if it's above 7, then it's basic. We can go from 0 to 14. That's the pH scale. A lot of 0 to 14. Okay, there's also a pOH scale. Okay, it's the opposite. Okay, if your pOH is between 7 and 14, okay, pOH now, then you're acidic. If your pOH is below 7, pOH now, then you're basic. So relationship between pH and POH is our next page in our notes. So just remember, when I'm saying a pH of 0, I'm talking about a concentration of 1 molar. Okay, how am I getting that? pH is equal to minus the log of the hydrogen ion concentration. Okay, which means that the hydrogen ion concentration is equal to 10 to the power of minus pH. Okay, these two are the same. Okay, so you can do the little calculator thing. In fact, let's do that. Okay, let's say my pH is 0. What is my concentration of H plus in moles per liter? All right, so we do the inverse log 10 to the power of minus pH. 10 to the power of, your pH is 0. Anything to the power of 0 is 1. Okay. How about if you have a pH of 3? Okay. So if our pH is 3, inverse log minus 3. Okay, everyone see how we're doing this on the calculator? Inverse log. And that's 0.001. Okay, 0.001. So same thing here, we can do the POH. Bless you. POH is minus the log of the OH minus concentration. The OH minus concentration hydroxide is 10 to the power of minus POH. So let's do this here. Okay, a POH of minus 14. So 10 to the power. The OH concentration is 1.00 times 10 to the minus 14. Let's do that here. Minus the log 1.00 times 10 to the minus 14. Okay, 14. So basically what I'm saying is you can go back and forth, okay, with your calculator. And another thing here is this times this. So right here, a different pen here. If you multiply these two guys together, you will get kW. kW is 1.00 times 10 to the minus 14. So let's put another column here where we multiply the concentration of H plus with the concentration of OH minus, and you'll see if you multiply these two all the way down, you'll get the same answer, 1 times 10 to the minus 14. And one final thing I want to tell you guys, we're talking about the pH and POH scale. Here the pH is increasing. Okay. While the pH is increasing, what's happening to the hydrogen ion concentration? Okay, it's increasing. So there's a inverse relationship here. Here the POH is decreasing, so it's increasing this way. If the POH is increasing this way, the hydroxide ion concentration is increasing the opposite way. Okay. So you guys see that? pH goes up, hydrogen ion concentration goes down. POH goes up, hydroxide ion concentration goes down. Okay. But, you know, the products of hydrogen ion and hydroxide ion stay the same. And they stay the same at that same value of Kw, which is 1 times 10 to the minus 14. Right? And don't forget, if we're below 7, we are acidic in pH. And if we are above 7, we are basic in pH. Okay? Talking about pH. We usually live in a pH-centered world, not a POH-centered world. All right, let's do some problems here. So get us into some numbers. All right, calculate the pH of a nitric acid solution having an H plus concentration of 0.76 molar. The first thing I want you guys to recognize is nitric acid is one of our 6 strong acids. Okay, it's one of our 6 strong acids. This is a very important point. So we do not need an ice table because it's a strong acid. Right? What other strong acids do not require an ice table? Okay, not just HNO3. Okay, but there's also H2SO4. There's also HCl. There's also HI. There's also HBr. And there's also, HClO4. Okay, so these are our 6 strong acids. Because they are strong acids, you can plug it right into the pH equation. Just plug it right in. Why? Because it's a strong acid, 100% H+. Okay, these strong acids will give you very close to 100% H+. Okay, very close to 100% H+. So we just plug it in. Okay, no ice table for any of these 6 strong acids. So pH is going to equal to minus the log of 0.76. Okay, we don't put units for pH. Okay, no units. So minus the log, minus log of 0.76. And the pH for that guy is 0.12. Okay, so that's pretty concentrated. 0.12. Okay, no units. Okay, no units. Well, the concentration, as you know, has units of molar, which is moles per liter, but our pH has no units. Okay, our pH has no units. It's a unitless dimension. So remember, strong acid, plug it straight in. How about this one? The pH of orange juice is 3.33. Calculate the hydrogen ion concentration. So here we're moving back, right? So first problem, we calculated the pH. In this problem, we're going backwards, okay? So we can go back and forth. Once again, pH is equal to minus the log of the hydrogen ion concentration. Okay, these two are the same. These two are the same thing, so one or the other is fine. But we are not calculating pH. Okay, they have already told us that this is 3.33. So we need to calculate H3O+. Okay, so the equation for that is H3O+ is 10 to the power of minus 3.33. So make sure you're comfortable going back and forth. So here we're going to do the anti-log. Anti-log 10 to the power of minus 3.33 and 0.00047, so 4.7 times 10 to the minus 4 molar. Now we put units here. Okay, now's the time we put units. The units are in moles over liter. Okay, so definitely put the units for the concentration. And here, pH, no units. Okay, no units for pH. It's a scale, and it's a unitless dimension. Concentration has units, big M, moles over a liter. Are these problems interesting or not? Maybe, sort of. Let's do another one here. We talked about orange juice. Let's talk about blood. Okay. The hydroxide ion concentration of a blood sample is 2.5 times 10 to the minus 7. What is the pH of the blood? Okay, the hydroxide ion concentration is this many moles per liter. What is the pH of the blood? So how shall we solve this here? There's two ways to solve it. Pick any one you'll want. I think I will calculate POH. Right, so POH is minus the log of the OH minus concentration. So minus the log of 2.5 times 10 to the minus 7. Okay, this is POH. Minus the log of 2.5 times 10 to the minus 7. Close those parentheses. 6.60. Okay, 6.60 is my POH. Wait, what is my pH then? Okay, that's POH. So realize that pH plus POH equals 14, correct? Bless you. Bless you, bless you. pH equals to 14 minus 6.60, and that is 5.4, 6.4, 7.4. 7.4. This is actually the right pH of blood, by the way. Okay? If your pH is a little bit off 7.4, I think the doctor or your physician, you guys know more. You guys are the future doctors. I think that's something that's wrong. I think you also work with it.
7.4.
Yeah, normal range, yeah. All right. One more problem with this, like this. Okay, which is more acidic? A solution where the H plus is 2.5 times 10 to the minus 3 molar, or a solution with a pOH of 11.6. Okay. So which is more acidic? So there's two ways to solve this. Let's either way is right. There's no wrong way. Which is more acidic? Okay, this one or that one. So here we have an H plus of 2.5 times 10 to the minus 3 molar. Here we have, so that's this, we'll do one here. This one has a pOH of 11.6. So let's figure out the hydroxide ion concentration. Okay, which is more acidic is what we're trying to answer. So pOH is equal to minus the log of the hydroxide ion concentration. The pOH is 11.6. So the hydroxide ion concentration, again, make sure you're comfortable going back and forth. Okay, cannot emphasize this enough. Make sure you're comfortable going back and forth. 10 to the power of minus 11.6, which equals to our hydroxide ion concentration. (2.51 times 10 to the minus 12 molar. That's the hydroxide ion concentration. So our H plus concentration is going to be K 1.00 times 10 to the minus 14 divided by 2.51 times 10 to the minus 12. Okay. Everyone know where I'm getting that? Okay, it comes from this. So I got our OH minus. Let's go ahead and get our H plus concentration from that. .00 times 10 to the minus 14 divided by 2.51 times 10 to the minus 12. And that's going to be 3.98 times 10 to the minus 3, big M. Okay, remember big M, concentration brackets, square brackets is big M. Square brackets is big M. All right, now you guys, which one is more acidic, 1 or 2? Something that's 2.5 times 10 to the minus 3, or 3.98 times 10 to the minus 3? Which has more H plus concentration? This guy, right? This is more acidic. There's another way to solve this problem. Okay. So what's the pH if your POH is 11.6? 14 minus 11.6 is 2.4. Okay, what's the pH here? Now I'm talking about an alternative way to solve this problem. .6. Okay, so which is more acidic? The one with the higher pH or lower pH? Lower pH, right? Below 7 is acidic. So also measuring by pH alone, we also find that this is more acidic. Okay. Remember, more H plus, lower the pH, more acidic. More H plus, lower the pH, more acidic. Okay, more H plus, lower the pH, more acidic. All right, let's talk a little bit about ice tables. Okay, what you see here are your strong acids. Okay, page 10 of our notes. Strong acids. So I'm talking about ice tables here, but really, strong acids do not need ice tables. So one thing here is, this is a good thing, right? No ice tables. Okay. No ice tables. For strong acids. Also, it's the same thing for strong bases, but also one thing for our 6 strong acids, look at the arrow. Okay, one way only. Okay, it's going in one direction. So if you see those 6 strong acids, it's going in one direction. I'm pointing at you. Okay, it's going 100% or close to 100% towards H plus. Okay, close to 100% H plus. Bless you. Okay, so a very good source of H plus, close to 100%, are your 6 strong acids. Once again, they are perchloric acid, hydrochloric acid, hydroiodic acid, hydrobromic acid, HBr, sulfuric acid, the first proton. Remember, sulfuric acid is diprotic, 2 protons. The first proton is strong, and then nitric acid. All right, so that's all we need to know for our strong acids. We plug it in straight to our pH equation. Plug it straight into pH equation, which is pH equals minus the log of H plus. All right, the weak acid situation is going to be different. The weak acids in our next page, we're going to use ice tables. Okay, in our next page, we see all of our weak acids, ice tables. Right? Unfortunately, we have to use ice tables. We did some ice tables in our quiz. We did some ice tables on our exam. Okay, anytime you see weak acids, everything else, we have to use ice tables. And then also I want to tell you guys one thing. Look at the arrows, right? One thing I'm kind of harping on, okay, to the point of maybe tiring you out. Okay, look at the arrows here. Okay, they go back and forth. Which means, are this 60% going to H plus, 70%, 40%? Okay, is it a 10% source of H plus? Okay, whatever it is, it's not 100%. Henceforth, it's a weak acid. You actually see, look at the equilibrium constants here. Okay, the equilibrium constants are less than 1. Okay, remember, if I had $1 million, am I moving forward in life? Okay, these are not $1 million acids. Okay, in fact, the Kas are much less than 1. Kas are less than 1. Okay, if I go back here to our strong acids, okay, these are $1 million acids. If I had $1 million, am I moving forward in life? Yes. Okay. If I had $1 million, I am moving forward in life. These all have Kas greater than 1. All right, so weak acids require ice tables. All right, let's go back to this here, the low ionization assumption. So there was a question on our quiz. I graded the quizzes in our last quiz where you had to use the quadratic equation. So while I said there'll be no quadratic equation on the test, I didn't say we'd have to do it on the quiz. So there was a question using the quadratic equation for one of the ice tables. So a couple of you got it right. But you'll realize that utilizing the quadratic equation is not the most, how should I put it, fun way. Okay, it's not the best way. A lot of work. Okay, unless you have a graphing calculator, like our friend Josh, he puts it into his graphing calculator, and he gets the answer. So when we do our ice tables for weak acids, do you want to use the quadratic equation? Okay, most of you will say no. Even I will want to say no. But this will tell us whether we can or not. And this is called the low ionization assumption. So remember, these are weak acids. Am I 40% going this way? Am I 50% going to protons? Am I 90%, 30%, 10%? Okay, to what extent is the reaction going in this forward direction? To what extent? Well, if it's less than 5%, okay, then you don't have to use the quadratic equation for our ice table. Okay, so we take our X from our ice table divided by the concentration of the acid given to us in the problem. Okay, multiplying it by 100 gives us the percentage. If that percentage of ionization is less than 5%, then the low ionization assumption works. Okay, you don't have to use the quadratic. If you do the same equation and it's greater than 5% ionization, that means you'll have to use the quadratic equation on your ice table. Okay, this is called the low ionization assumption. We'll do a practice problem like this here. Okay. In fact, let's do one now. So here we're going to use the low ionization assumption. Okay, remember this formula here. Keep it in the back of your mind. Okay. What is the pH of a 0.122 molar monoprotic, that means 1H plus monoprotic acid whose Ka is 5.7 times 10 to the minus 4? Okay, so the first thing we'll do is it's a weak acid. How do I know it's a weak acid? It's not one of our 6, number 1. It's not one of our 6. Number 2, okay, you look at the Ka value, it's pretty small, 10 to the minus 4. Right? So let's write our equation here, HA plus H2O. This is something that you guys must know how to write for any quiz or exam. Here the Ka is 5.7 times 10 to the minus 4. Okay. All right, here's our ice table now. Okay, we start out with 0.122. We start out with 0.122 and 0 of H3O plus and 0 of A minus. Some of it is going to go this way because it's in equilibrium. It's a weak acid. It does not, these equilibrium reactions never go to 100% completion. So it's going to be minus X, plus X, and plus X. The reaction is going this way. Initially we had 1.22. Finally we will get a little bit of this and a little bit of that and a little bit of this. Remember, equilibrium doesn't go to 100% completion. So at equilibrium we have 0.122 minus X plus X plus X. All right, let's put this into our Ka. Equals products over reactants Our Ka is 5.7 times 10 to the minus 4. Concentration of H3O plus is x. Concentration of A minus is x. So x times x is going to be x squared divided by 0.122 minus x. Okay. And now we will use our low ionization assumption. What is that? What is our low ionization assumption state? We'll call it LIA for low ionization assumption. Okay, we will assume x is small. And 0.122 minus x is about 0.122. So let's think about it. It's not going totally this way. Okay? It's very, very small. This x, the extent to which this is going this way is very, very small. It's so small that 0.122 minus x is just essentially 0.122. It's very small. It's not going this way, but it's going maybe this way. Okay? Very little. Instead of going this way, it's going this way. We're assuming it's going this way. Very little extent going. Okay, that's what the assumption states. So using this assumption, we have 5.7 times 10 to the minus 4 is equal to x squared divided by 0.122. Okay, this will save us a lot of headache and hassle. I'm going to use the next page here. So continuing on. Okay, so here's our low ionization assumption. Okay, once again, assume 0.122 minus x is about 0.122. This is the low ionization assumption. All right, so now we'll solve for x. (5.7 times 10 to the minus 4 times 0.122). Okay, let's square root this to get x. Okay, so I combined a couple of steps here to go from the pink to the green. (5.7 times 10 to the minus 4 is that times 0.122). Okay, let's square root this. Getting 0.00834 big M. Here gets units of big M. So is this our value of x that we plug in back in here? Well, let's see if our assumption is correct. Okay, so here the assumption is that if the percent ionization is less than 5%, that is a significantly weak acid, low ionization. We don't have to solve for x using the quadratic. So x here we got. So let's test our low ionization assumption. So x we got in this problem, we got 0.00834. Okay, divided by what's the concentration initially of our acid? The concentration initially of our acid is 0.122. Okay, that's how much we started off with. So x is what we got from the ICE table after our assumption. The initial concentration is 0.122. We make that a percentage by multiplying it by 100. Let's see what we get here. So 0.00834 divided by 0.122 times 100, 6.8%. Did our assumption work? Okay. Remember, 5% is our threshold. 5% is our cutoff. We did this and we got 6.8% ionization. Okay. Is this the right answer for X? Okay, no, we have to use the quadratic. So our assumption failed. We have to use the quadratic. We're not going to do that, but this is what the low ionization assumption is. Okay. Assumption did not pass. Must use quadratic here. So that's just how it goes sometimes. This is an acid whose concentration is significant enough that this math cannot be simplified, that you'll have to do the quadratic, solve for X utilizing the quadratic equation here. And I think in our next page in our notes, I went ahead and did all of that and solved it, but I'm not going to go over it for now. All right, but here you'll have to use the quadratic. So that's the low ionization assumption, and for the most part, use that. I can tell you that for the exam, my exams, you'll probably not have to use the quadratic. Okay, so you won't have to use the quadratic. The low ionization assumption for weak acids will be when you do that test, will be below 5%, and you're safe with the assumption. All right, so I think I'll stop class for today, and we'll resume on Wednesday. So have a good day, everyone. See you on Wednesday.